Good morning, children. This is 12th Physics. We are doing chapter number 6, Electromagnetic Induction. Today we are going to cover the topic that is self-induction and self-inductance. So let's start with it. So children, self-induction, right? So now we know, children, that when we pass current through a coil, magnetic field is produced, right? If you pass current through this coil, magnetic field, that is B, will be produced in the coil. Now due to this magnetic field, the magnetic flux will be linked in the coil. The magnetic lines will be passing through the coil, right? So due to the magnetic field, magnetic flux will also be produced. Now children, if we change the magnitude of the current, if we change the current, then the magnetic flux that is linked with the coil will also change. And as the magnetic flux changes, according to Faraday's second law, an EMF or current will be induced in the coil. So what is it? That when we pass current through the coil, magnetic field is produced. And as magnetic field is produced, the magnetic flux will be linked with the coil. And if we change the current in the coil, then the magnetic flux will also change and an EMF or current will be induced in the coil, right? Here the induced EMF or the current that is produced due to the change in the magnetic flux of the coil itself. Here we are changing the current in the same coil and magnetic flux linked with the coil changes and EMF is induced in the coil. EMF or current is produced in the coil. So it is because of the coil itself. So this phenomena is known as self-induction. So what is it? An induced EMF or current is produced due to the change in the magnetic flux of the coil itself. This phenomena is known as self-induction. Right, children? And here the direction of the induced EMF can be found in accordance with the Lenz law. Now, what is Lenz law? We should be knowing now. Lenz law, according to Lenz law, the direction of the induced EMF or the current will be such that it opposes the reason of its production. Right, children? Okay. Now, let's talk. For example, here we can see that if I increases, if the current in the coil increases, then the magnetic field will also increase. And as the magnetic field increases, the flux that is linked with the coil will increase. So as the flux is changing, as the flux is increasing, an EMF or current will be induced in the coil. Right, children? So what will be its direction? So what is the reason of production of induced EMF or current? The reason is increase in the magnetic flux. So the direction of the induced EMF or the current will be such that it will oppose the increase in the current in the coil. So what will happen, children? In this, the current, suppose this is your coil, right? The current which is flowing in the coil is in, suppose, this direction. So as the current is increasing, the EMF that will be produced, the current that will be produced will oppose the increase in the EMF, increase in the current. So your EMF E will be in direction opposite to the direction of flow of current. That is, it is opposing the increase in the current, right, children? Now let's talk about the other case. About the other case is, if the current I is decreasing, then we know, children, magnetic field will decrease and the flux linked with the coil will decrease. So as the flux is decreasing, right, as there is change in the flux, so EMF or current will be produced in the coil. What about the direction? Its direction will be such that it opposes the decrease in the current, it opposes the decrease in the flux. So it will oppose the decrease, means it will try to increase it. So in this case, children, if this is your coil and this is the direction of current. Now the current is decreasing, so now the current that is produced, now the EMF that is induced will be such that it will try to increase it, because current is decreasing now. So the EMF or the current that is produced in the coil will oppose the decrease and it will try to increase. So it is along the direction of the current, right? So the direction of the induced current will be in the direction of the current I, or the applied current I. So children, here we can see that the flux phi is directly proportional to current. If the current increases, that is, the flux through the coil is directly proportional to the current flowing through the coil. And children, we know if we remove the proportionality sign, then a constant will appear, and here the constant is L. Here L is known as the self-inductance. Here L is known as self-inductance. L is known as self-inductance, or it is also called as coefficient of self-induction of the coil. Right. So what is self-inductance? Self-inductance is a property of the coil, right? To do what? To oppose the change in the flow of current in it. Right? It will oppose the change in the flow of current in it. If the current is increasing, it will try to decrease it. And if the current is decreasing, it will try to increase it. So it is not in favor of the change. It will always try to oppose the change of flow of current in the coil. So self-inductance, that is a property of the coil to oppose any change in the flow of current in it. So if the value of L is more, if the value of L is more, then children, the induced EMF will be more. Induced EMF will be more means opposition to the change in current will be more. Right, children? Now, here, if we put I equals to 1, if we put I equals to 1 ampere, then the flux is equal to, magnetic flux is equal to the self-inductance, right? So children, here comes the definition of self-inductance. Here you can use this as definition of self-inductance is that if 1 ampere current flows through a coil, then the self-inductance L is equal to magnitude of magnetic flux linked with the coil, right children? So here L does not depend on current. L depends upon the number of turns. How many turns are there in the number of turns of the wire, right children? Next, it depends upon the cross section area of the coil, right? More the cross sectional area, more will be the self inductance, and it depends upon the nature of the material on which the wires on which it has been wound, right children? Now what about the magnitude of the produced EMF? So magnitude of the induced EMF will be given by Faraday's second law, that is E equals to minus d phi by dt. And if we put the value of phi from here, we will get E equals to minus d by dt of Li. But here L is self-inductance whose value is constant. So L will come out of the differentiation and you will have E equals to, that is the EMF produced, the induced EMF is equals to minus L di by dt. Okay children, so this is the magnitude of EMF produced in the coil due to the phenomena of self-induction. Now let's talk about another term, that is self-inductance. Self-inductance of a solenoid. So children, for self-inductance, now we know that on passing current through a solenoid, when you pass current, what will happen? Magnetic field is produced, and as magnetic field is produced, magnetic flux will be linked with the solenoid. Now if we change the current, if we change the current, then what will happen? The magnetic field will change. The magnetic flux, which is linked with the solenoid, will change. And as there is a change in the magnetic flux, an EMF or current will be produced in the solenoid according to your electromagnetic induction principle, right? And that EMF, the direction will be in accordance with the Lenz's law, right? That is, it will try to, the EMF produced will be such that it will oppose the reason of its production, right? Now what we are doing, we are increasing the value of I. So as we are increasing the value of I, the induced EMF will be such that the current that will be produced, the EMF that will be produced, will be, its direction will be such that it will oppose the change in the current. So it will oppose the increase in the current, right? So it will flow in the opposite direction and making it less, making it, stopping it from increasing, right? So this property of solenoid, to oppose the change in the flow of current through it, is known as self-inductance. So self-inductance, if the self-inductance is more than the magnitude of EMF that is produced, if the self-inductance is more, then the magnitude of EMF that is produced will be more, and opposition to the change in the flow of current will be more. And if the self-inductance is less, if the value of self-inductance is less, then the magnitude of EMF produced will be less, or the opposition hoga to the change in the flow of current will be less. Right, children? And here, when we pass current, magnetic field B is produced in the solenoid. Now, the magnitude of that magnetic field is B equals to mu 0 Ni, where mu 0 we know it is the magnetic permeability of free space, right? And here N is, here capital N is the total number of turns and L is the length of the conductor. So can we calculate the number of turns per unit length? So what it will be? It will be total number of turns upon the total length. So small n is the number of turns per unit length. एक one unit length में कितने turns हैं? And n are the, capital N are the total turns, right? So here we can replace, instead of small n, we can put capital N upon L. Now we know the magnetic flux that is linked with the coil will be equal to phi equals to N B dot A. Now if we remove the dot, it will be cos theta, where theta is the angle between the magnetic field B and the area vector of the solenoid. So if we see, children, the magnetic field B is in this direction, the area vector of this face will be along the same direction. So the angle between them is 0. So here we are going to substitute the value of theta as 0, and we can put the value of B from here, right? And that is this value, we will substitute it over here. So on substituting the value of B and theta as 0, cos 0 is 1, so the flux phi will be equal to mu 0 capital N square IA upon L. Now we want to find it in terms of, now we know the self-induction L, right, in terms of magnetic flux is phi upon I. Just now we did phi upon I. So substitute the value of phi, you'll get this. So L equals to mu 0, I will get cancelled, N square A upon L. So here mu 0 is there because we have considered that the medium between them is either air or it is vacuum. But if you are having some medium, then the mu naught will be replaced by mu. That would be the magnetic permeability of the given medium. Right, children? So this is your self-inductance of a solenoid. So self-inductance, that is the property of the solenoid to oppose the change in the flow of current through it. That is your self-inductance. It does not depend upon the current that is flowing through the conductor. It depends upon the number of turns. It depends upon the medium. It depends upon the cross-sectional area of the solenoid, and it depends upon the length of the solenoid. And here, as you can see, it is inversely proportional to length. So if the length is less, the self-inductance will be more, and all other properties, it is directly proportional.